All right, so this next section is, it's going to be a little bit change of pace from sections 1 and sections 2. We're transitioning to looking at 3 different types of variation: direct variation, inverse variation, and joint variation. And there's a method to the madness here. The inverse variation is very closely related to these rational expressions that we've been working with, okay? So first, let's just look at the 3 types and their formulas or their equations. The first type you should have some experience with probably from Algebra 1. It is known as direct variation, and it would follow this format. Y equals k times x, where k is known as our constant of variation, okay? Now, whenever we're working with variation, we're trying to make a comparison between two or more variables, okay? So the mark of direct variation, at least in a real world situation where everything is positive most likely, for 2 variables to vary directly, as one value gets bigger, the other's going to get bigger, okay? So if I make x a larger number, as x increases, y is going to increase as well in a direct variation situation, okay? So let me give you a more concrete example here. Y equals 2x. All right, now that's just a linear equation. It's in slope-intercept form. It's got a y-intercept of 0, and it's got a slope of 2 over 1. So you rise 2, you run 1. You can fill up the graph with several points. All right, so again, the idea here on direct variation is if I make x bigger, y is going to get bigger as well, all right? And there's a lot of real-world variables related to each other directly. For example, your height and your shoe size. You would expect, if you collected data across this room, that the taller the person, the bigger their shoe size is going to be, right? Okay, those 2 variables would vary directly then. Okay, now the next type is inverse, and it would be y equals k divided by x. All right. Now in inverse variation, it's the opposite of direct. As one variable gets bigger, the other gets smaller. Okay, so let's give you an example of this one. Y equals, let's do 4 over x. I'm making k that constant of variation 4. All right, now notice this has a rational expression built into it. We've got 4 over x here. That's a rational expression. Okay, so that's kind of how it fits into, you know, what we're working with in this whole unit, all right? And now think, the larger I make x, since I'm dividing by it, the smaller the y is going to be, okay? Now, we don't have any experience graphing these. The graph actually has 2 parts to its curve, okay? Now, here's another way you can look at this, and I think it's really helpful for when you go to graph it. Y equals 4 over x is the same as xy equals 4. X times y equals 4, right? So when I see it in that form, I know that the points that are going to be on this graph, their x and y coordinates have to multiply together to make a 4, okay? So let's do a quick little table of values and think about some possibilities on that. If x is 1, y would have to be 4 for those to multiply together to be 4, right? So I have a point of 1, 4. I could switch it. I could say x is 4 and y is 1. Those would multiply together to give me 4. Give me two other numbers that multiply to 4.
2 and 2.
2 and 2. Okay, now we could continue this with other pairs of numbers. And if we did, we would see this kind of pattern to the points. Okay, now that's only half the graph though. What we haven't considered is that there's pairs of negative values that multiply to 4 as well. So I could take that table that I already created and I could change all the coordinates to being negative. -1, -4. If I multiply those together, I still get +4, right? Or -4, -1. Or -2, -2. So that's the second half of the curve. This is what a typical rational function looks like. It has two parts to its curve. And then there's also a couple what we call asymptotes. We heard that word before? Asymptote? Yes, no? All right, so an asymptote, let's write that in. Here's how you spell it. Asymptote. That is a line that your curve approaches, but it never actually touches. So the green curves here, they're getting infinitely close to these two asymptotes. Okay? Now notice where the asymptotes are placed. They're placed at y equals 0 and at x equals 0. And there's a reason they're there. Okay? Look back at the original formula, y equals 4 over x. X is not allowed to be 0. X is your undefined value. Or 0, I should say, is your undefined value. And then I could say the same thing for y as well. Y is not allowed to be 0 either. That's why we have those two asymptotes. All right, now the good thing is we're not going to really have you doing any graphing right now. Okay, this is just an introduction into what the graph would look like. We care more about can we use the formula for inverse variation more than anything right now. In the mark of inverse variation, as one variable gets bigger, the other gets smaller. Okay? All right, then there's joint variation. Joint variation is kind of an extension of direct variation in 3 dimensions. So here is, that's direct variation, right? Y equals kx. Joint, you would just have to throw in a z. Y equals k times x times z. By throwing in the third variable there, that means you're in 3 dimensions. Okay? And we're not going to worry about graphing something like that. Yeah, we've done a little 3D graphing, but not much. So we don't want to get too involved right now with that. All right, so example 1. Suppose y varies directly as x. So that statement is key, especially the word directly. That tells me to use this formula, our direct variation formula. We are told that y is -15 when x is 5, and we need to use that pair to come up with y when x is 3. So I like to treat this like a 2-step process. I plug in -15 for y, and I plug in 5 for x. Solve for the constant of variation k, you get -3. So the overall model for this scenario would be y equals negative 3x. And I can now use that to figure out y when x is 3. So I substitute a 3 in. Y ends up being negative 9. Questions there? All right, example 2 is very similar, but now we're using joint variation. We are varying jointly, so that tells me y is equal to k times x times z. I want to know what y is if x were 10 and z were 5. By also knowing that when y is 12, z has to be 8 and x has to be 3. So I use the second half of that statement there to get my k. Y is 12 when x is 3, z is 8. Solve for k. Ends up being 1/2. All right, so my model overall for this situation is y equals 1/2 times x times z. Now let's get y when x is 10 and z is 5. That's going to multiply out to 25. Questions there? All right, then the last one. R varies inversely as t. R would equal k divided by t then if they vary inversely. R is negative 6 when t is 2. What's that make k? Negative 12, yeah, multiply both sides by 2. K is negative 12. So our formula overall for this situation is R equals negative 12 divided by t. Okay, so now find R when t is negative 7. But the only thing I can do with that is divide the negatives away, right? 12/7 would be R.